A frozen moon, smaller than the state of Arizona orbiting silently around Saturn, is shooting massive jets of water into space. But hidden inside those icy plumes, scientists have detected something extraordinary. Organic molecules, salt-rich ocean water, complex carbon compounds, and enough chemical energy to support life, which raises a possibility that sounds almost unbelievable. The first alien life we discover might not be on a distant planet orbiting another star. It might be hiding inside a small icy moon, quietly circling Saturn in the outer solar system. The moon is called Enceladus. For most of modern astronomy, Enceladus was considered unremarkable. Discovered in 1789 by the British astronomer William Herschel, it appeared to be just another frozen satellite, a bright icy sphere only about 500 kilometers wide. Compared with massive moons like Titan or Ganymede, Enceladus seemed insignificant. It reflected sunlight strongly because its surface was covered in fresh ice, making it the most reflective object in the solar system, but otherwise it looked cold, quiet, and geologically inactive. For decades, scientists assumed it was little more than a frozen rock drifting through space. But that assumption began to change in the early 2000s when a spacecraft arrived at Saturn after traveling nearly 7 years through deep space. That spacecraft was NASA's Cassini mission, one of the most ambitious planetary exploration projects ever launched. Cassini entered Saturn's orbit in 2004 and began studying the planet, its rings, and its many moons in extraordinary detail. At first, Enceladus was simply one of many targets on Cassini's schedule. But as the spacecraft began collecting data, something strange appeared. Instruments measuring heat detected an unexpected warm region near the moon's south pole. In the freezing darkness nearly 1.5 billion kilometers from the sun, warmth on a small icy moon was surprising. Then Cassini's cameras revealed something even more astonishing. Towering plumes of water vapor were erupting from cracks in the surface, blasting ice particles and gas hundreds of kilometers into space. These plumes were not small geysers. They were enormous jets of material, constantly spraying out of the moon like natural fountains, powered by an unseen ocean beneath the ice. Scientists quickly realized this discovery was extraordinary, because those plumes meant something important. Liquid water existed inside Enceladus, and not just small pockets. Evidence suggested a vast underground ocean hidden beneath the moon's frozen crust. Suddenly, Enceladus transformed from a quiet frozen moon into one of the most fascinating worlds in the solar system. The reason scientists became so excited about this discovery is simple. Life, at least the kind we understand, depends on a few key ingredients. First, there must be liquid water. Water is essential for chemical reactions inside living cells. Second, there must be energy, because life requires a continuous source of power to maintain biological processes. And third, there must be organic molecules, the carbon-based compounds that form the building blocks of life. Enceladus appears to have all three. The plumes detected by Cassini contained water vapor, tiny ice grains, salts, methane, carbon dioxide, ammonia, and complex organic molecules. These ingredients were not just traces, they were abundant enough to suggest an active chemical system inside the moon's hidden ocean. But perhaps the most important discovery came when Cassini detected microscopic particles of silica in the plumes. On Earth, silica particles of that specific size and composition form only in one type of environment: hot water interacting with rock at the bottom of the ocean. In other words, hydrothermal vents. On Earth, hydrothermal vents are found along mid-ocean ridges where volcanic activity heats seawater deep below the surface. Superheated water rich in minerals flows out of cracks in the ocean floor, creating an environment filled with chemical energy. These vents support entire ecosystems that exist without sunlight. Strange tube worms, blind shrimp, bacteria, and complex life forms thrive there using chemical reactions instead of photosynthesis. If similar hydrothermal systems exist inside Enceladus, they could provide both energy and nutrients for microbial life. But how can such a small moon remain warm enough to maintain a liquid ocean? The answer lies in a process known as tidal heating. Enceladus orbits Saturn in a slightly elliptical path, meaning the distance between the Moon and the giant planet constantly changes during each orbit. Saturn's immense gravity stretches and compresses Enceladus as it moves along this path. This repeated squeezing creates friction inside the Moon's interior. That friction generates heat. Even though the Moon is surrounded by the cold vacuum of space, the internal heating caused by Saturn's gravity can melt ice deep beneath the surface. Over time, this heating likely created a global ocean trapped beneath a thick shell of ice. The outer crust may be tens of kilometers thick in some places, but near the South Pole, the ice appears thinner. There, enormous fractures known as tiger stripes slice across the surface. These fractures act like giant vents connecting the underground ocean to space. Pressurized water from the ocean rises through these cracks and erupts outward, as the geysers Cassini observed. Each eruption releases ice particles, vapor, and chemical compounds from the ocean below. In other words, Enceladus is naturally delivering samples of its hidden ocean directly into space. Cassini took advantage of this remarkable situation. During several daring flybys, the spacecraft passed directly through the plumes themselves. As it flew through the icy spray, instruments analyzed the particles and gases in real time. It was like flying a laboratory through an alien ocean without ever landing on the surface. The data collected during these flybys transformed our understanding of the Moon. Scientists detected sodium salts in the plume particles, indicating that the water had been in contact with rock deep inside the Moon. The chemical composition suggested the ocean was salty, similar in some ways to Earth's oceans. Cassini also detected molecular hydrogen in the plumes, which is especially important. Hydrogen gas can serve as a powerful energy source for microbes. On Earth, certain microorganisms use hydrogen to produce energy through metabolic reactions. These microbes form the base of entire ecosystems in deep-sea hydrothermal vent environments. If hydrogen is being produced inside Enceladus through interactions between water and rock, microbes could potentially use that hydrogen as fuel. Yet despite all this evidence, scientists remain cautious. Organic molecules do not automatically mean life exists. Chemistry can produce complex carbon compounds without biology. Methane can form through geological processes, and hydrogen can be generated by chemical reactions in rocks. So while Enceladus has many of the ingredients needed for life, no direct evidence of living organisms has been found. Another important question involves time. For life to develop, stable conditions must exist for long periods. On Earth, the earliest microbial life appeared relatively quickly after the planet cooled, but it still required millions of years. If Enceladus's ocean formed recently in geological terms, there may not have been enough time for life to emerge. Some models suggest the ocean could be billions of years old, while others propose it may be much younger. Determining the age of the ocean remains one of the biggest unanswered questions about the Moon. Even without confirmed life, Enceladus has already reshaped how scientists think about habitable environments. For most of the 20th century, researchers assumed that habitable worlds had to be located within a star's habitable zone, the region where temperatures allow liquid water on a planet's surface. Earth lies comfortably within the Sun's habitable zone. Mars sits near the outer edge. But Enceladus exists far beyond that region, in a place where sunlight is extremely weak. Yet it may still host a warm ocean because internal energy replaces solar heat. This discovery means habitable environments might exist in places we never considered before. Icy moons warmed by tidal heating could potentially support subsurface oceans even when they orbit far from their stars. And Enceladus is not the only example. Jupiter's moon Europa likely contains a vast ocean beneath its icy crust. Saturn's largest moon Titan may hide an internal ocean as well. Even distant dwarf planets such as Pluto may have liquid water oceans buried beneath frozen surfaces. If subsurface oceans are common, the number of potentially habitable environments in the solar system increases dramatically. Instead of only a few candidates like Mars, we may have multiple ocean worlds capable of supporting life. Among these worlds, Enceladus stands out for one important reason. Accessibility. Most ocean worlds are sealed beneath thick ice crusts that would be extremely difficult to penetrate. Drilling through kilometers of ice on another world would require complex technology. But Enceladus conveniently sprays its ocean into space through its plumes. A spacecraft does not need to land or drill, it can simply fly through the plume and collect samples. Future missions could carry instruments specifically designed to detect biological molecules such as amino acids, cell-like structures, or chemical patterns associated with metabolism. Some mission concepts even propose capturing plume particles and returning them to Earth for laboratory analysis. The technology required for such missions is already under development. Space agencies are seriously considering future exploration of Enceladus because of its extraordinary potential. If a future mission detected clear signs of microbial life, the discovery would be revolutionary. It would mean life emerged independently in at least 2 places within the same solar system. That would strongly suggest life is not rare in the universe. Instead, it might arise wherever the right conditions exist. Such a discovery would change not only science, but humanity's understanding of its place in the cosmos. For centuries, humans wondered whether we are alone. Philosophers debated the possibility of life beyond Earth long before telescopes existed. Today we know the galaxy contains hundreds of billions of stars and likely trillions of planets. Astronomers have already discovered thousands of exoplanets orbiting distant stars. Many of those planets exist in habitable zones where liquid water might exist. But detecting life on distant planets is extremely difficult. Even our most advanced telescopes can only analyze faint signals from their atmospheres. Enceladus, however, is right here in our cosmic neighborhood, only about 1.5 billion kilometers away, close enough for robotic missions to explore directly, close enough that the answer to one of humanity's oldest questions might be waiting beneath its icy crust. Right now, Enceladus continues its silent orbit around Saturn, completing a full revolution roughly every 33 hours. Its bright icy surface reflects sunlight like a mirror while powerful geysers continue to erupt from the South Pole. Those plumes feed Saturn's E-ring, a vast ring of icy particles surrounding the planet. Every eruption carries tiny fragments of the ocean into space, each one containing chemical clues about the hidden world below. Scientists are still studying the data Cassini sent back before its mission ended in 2017, when the spacecraft deliberately plunged into Saturn's atmosphere. Even years after the mission ended, researchers continued to analyze the measurements collected during those plume flybys. New insights continue to emerge, revealing more about the chemistry, temperature, and structure of Enceladus's ocean, and with every discovery, the possibility of life remains on the table. Somewhere beneath kilometers of ice, an alien ocean may be circulating through a rocky core warmed by tidal forces. Hydrothermal vents may be releasing hydrogen and minerals into the dark water. Chemical reactions may be providing energy in the absence of sunlight. And within that hidden ocean, microscopic organisms might already exist, thriving in conditions similar to the deepest parts of Earth's oceans. If that is true, then life has found a way in 2 completely separate environments on the same solar system. One bathed in sunlight on Earth's surface, and another buried in darkness beneath ice on a distant moon. That realization would suggest something profound about the universe. Life may not be a rare accident. It may be a natural outcome of chemistry and physics whenever water, energy, and the right elements come together. Across the galaxy, there could be countless ocean worlds like Enceladus, each hiding its own ecosystems beneath frozen surfaces. For now, we do not know what lies within that ocean. It may contain nothing more than water and chemistry, or it may contain the first alien life humanity will ever discover. And until another spacecraft returns to explore those plumes again, the mystery of Enceladus remains unsolved, waiting quietly in the cold darkness of Saturn's orbit, its hidden ocean still erupting into space, still sending signals from the depths of an alien sea.